right. Okay. Welcome one, welcome all. I hope you're having a wonderful day so far. Today is September 17th, 2025, and we're going to be jumping back into Introduction to Algorithms today. Yay! Okay. All right, let's go ahead. Close my door. Hot in here though. All right. Let's get back into today. All right, let me start recording here. All right, hello everybody, welcome back in and thanks for joining me and welcome back to the channel. Today we're going to be jumping back into Introduction to Algorithms 4th edition. This is going to be the part 3, or I don't need to actually do an intro because this is going to be a continuation of the last streams, right? So, being done. Let's go back down. Here. All right. Okay, let's get jumping into this. 4.6, Proof of the Continuous Master Theorem. Proving the Master Theorem, Theorem 4.1, in its full generality, especially dealing with the knotty technical issues of floors and ceilings, is beyond the scope of this book. This section, however, states and proves a variant of the Master Theorem, called the Continuous Master Theorem, in which the master recurrence, 4.17, is defined over sufficiently large positive real numbers. The proof of this version, uncomplicated by floors and ceilings, contains the main ideas needed to understand how master recurrences behave. Section 4.7 discusses floors and ceilings and divide and conquer recurrences at greater length, presenting sufficient conditions for them not to affect the asymptotic solutions. Of course, since you need not understand the proof of the master theorem in order to apply the master method, you may choose to skip this section. But if you wish to study more advanced algorithms beyond the scope of this textbook, you may appreciate a better understanding of the underlying mathematics which the proof of this continuous master theorem provides. Yeah, the screenshots that I have in here of my notes. Um, Although we usually assume that recurrences are algorithmic and don't require an explicit statement of a base case, we must be much more careful for proofs that justify the practice. The lemmas and theorem. What is that? The lemmas? I've never heard of that word before. And theorem in this section explicitly state the base cases because the inductive proofs require mathematical grounding. It is common in the world of mathematics to be extraordinarily careful proving theorems that justify acting more casual in practice. The proof of the continuous master theorem involves two lemmas. Lemma 4.2, or is it lemma? Probably lemma. The proof of the continuous master theorem involves two lemmas. Lemma 4.2 uses a slightly simplified master recurrence with a threshold constant of n not equal to 1, rather than the more general n not greater than 0 threshold constant implied by the understated base case. The lemma employs a recursion tree to reduce the solution of the simplified master recurrence to that of evaluating a summation. Lemma 4.3 then provides asymptotic bounds for the summation, mirroring the three cases of the master theorem. Finally, the continuous master theorem itself, theorem 4.4, gives asymptotic bounds for the master recurrences, while generalizing to an arbitrary threshold constant n not greater than 0 as implied by the unstated base case. Some of the proofs use the property described in problem 3-5 on page 72 and 73 to combine and simplify complicated asymptotic expressions. Although problem 3-5 addresses only big theta notation, the properties enumerated there can be extended to big O notation and big omega notation as well. Here's the first lemma. Lemma 4.2. Let A be greater than 0 and B be greater than 1 and be constants. And let f of n be a function defined over real numbers, n greater than or equal to 1. Then the recurrence, t of n, is equal to theta of 1 if n is between or equal to 0 and less than 1, as well as the recurrence if n is greater than or equal to 1 of t times f of n over b plus and a recurrence if n is greater than or equal to 1 of the constant a times the recurrence t of n over b plus f of n, and has a solution, right? T of n equal to theta n to the power of log base b times a plus the sum, right, for all values of j starting at 0 up to the floor log b of n, right, the a constant to the power of j times f of n over b to the power of j. Proof. Consider the recursion tree in figure 4.3. Let's look first at its internal nodes. The root of the tree has cost f of n, and at its a children, each with cost f of n over b. It is convenient to think of a as an integer, especially when visualizing the recursion tree, but the mathematics does not require it. Each of these children has a children making a squared nodes at depth 2, and each of the a children has a cost of f of n over b squared. In general, there are a to the power of j nodes at depth of j, and each node has a cost of f of n over b to the power of j. Now let's move on to the understanding of the leaves. The tree grows downward until n over b to the power of j becomes less than 1. Thus, the tree has height of the floor log base b of n plus 1. Because n over b to the power of that floor value of log base b times n is greater than or equal to n over b to the power of log base b times n, which is equal to 1. And n over b to the power of floor log base b times n plus 1 is less than n over b to the power of log base b of n, which equals to 1. Since we have observed the number of nodes at depth j since we have observed the number of nodes at depth j is a to the power of j, and all the leaves are at depth floor log base b of n plus 1, the tree contains a to the power of log base b plus n the tree contains a to the power of log base b times n floored plus 1 leaves. Using the identity 3.21 on page 66, we have this new identity rearranged to equal big O of n to the power of log base b times a. Since a is a constant, and a, right, is proven to be since a is a constant and a to the power of log base b times n floor plus 1 is greater than or equal to a to the power of log base b times n, which equals to n to the power of log base b times a, which equals to big omega of n to the power of log base b times a. Consequently, the total number of leaves is big theta of n to the power of log base b times a. Asymptotically, the watershed function. We are now in a position to derive equation 4.18 by summing the cost of the nodes at each depth in the tree as shown in the figure. The first term in the equation is the total cost of the leaves. Since each leaf is at the depth of floor log base b times n plus 1, and n over b to the power of log base b times n floored plus 1 is less than 1, the base case of the recurrence gives the cost of a leaf equal to big theta of 1. Hence, the cost of all big theta n to the power of log base b times a leaves is, right, big theta of n to the power of log base b of a by problem 3-5D. The second term in equation 4.18 is the cost of the internal nodes, which is the underlying divide and conquer algorithm. Represents, oh my gosh, the second term in the equation the second term in equation 4.18 is the cost of the internal nodes, which, in the underlying divide and conquer algorithm, represents the costs of dividing problems into subproblems. And, as we'll see in the three cases of the master theorem, depend on the distribution of the total cost across the levels of the recursion tree. So let's take a peek back here at this recursion tree here above, where we have some function f of n, and it spans a children, right? You're multiplying the recurrence, right, the reduction of n until we reach some base case by some value a to basically know how much it is, how many branches are happening at each, division, right? So we're doing a times this new recurrence of f of n over b to get to the next depth level, right? And then to find the levels after that, you just raise those values to a power corresponding to the depth at a one index, right? Or, right? So j of 0, which gives you the value, right? To the power of. So actually starting from 0, power of 1, power of 2, power of 3, but obviously we hit the base case here. Interesting. Let's just quickly throw this into here. Can you explain The kind of occurrence is exactly the form you'll see in divide and conquer algorithms. We split the problem of size n into a subproblems, each with a subproblem size of n over b. And we pay an additional cost, f of n, for splitting / combining work. Right, that's this plus f of n here. Visualizing the recursion tree. The recursion tree helps us see where costs come from. At the root level 0, the cost is f of n. Right? At depth 1, we have a subproblems of n over b size, with a total cost of a times f of n over b. At depth 2, we raise those values to the power, right? So the internal node costs, right, are the sum from 0 all the way up until the floor of log base b times n of a to the power of that j value times f of n over b to the power of that j value for the depth, right? So the recursion stops when the subproblem size n over b to the power of j is less than 1. So just by rearranging this happens when j is greater than this. So the height of the recursion tree is about this. Okay. As we'll see, the three cases of the master theorem depend on the distribution of the total cost across levels of the recursion tree. Case 1, the cost increased geometrically from the root to the leaves, growing by a constant factor with each level. Case 2, the costs depend on the value of k in the theorem. With k equal to 0, the costs are equal for each level. With k equal to 1, the costs grow linearly from the root to the leaves. With k equal to 2, the growth is quadratic, and in general, the costs grow polynomially in k. Case 3, the costs decrease geometrically from the root to the leaves, shrinking by a constant factor with each level. The summation in equation 4.18 describes the cost of the dividing and combining steps in the underlying divide and conquer algorithm. The next lemma provides asymptotic bounds on the summation's growth. Is it lemma or lemma? Lemma. Emma. Lemma. Yeah. Lemma 4.3. Let a be greater than 0 and b be greater than 1 and be constants. Let f of n be a function defined over real numbers, n is greater than or equal to 1, then the asymptotic of the behavior of the function is this, defined for n greater than or equal to 1, and can be characterized as follows. If there exists a constant epsilon greater than 0, such that f of n is equal to big O of n to the power of log base b times a minus that epsilon, then g of n is equal to big O of n log to the power of log base b times a. If there exists a constant k that is greater than or equal to 0, such that, right, proving for big theta, if there exists a constant c in the range of 0 to c to 1, such that 0 is less than a times f of n over b, which is less than or equal to c times f of n for all n greater than or equal to 1, then g of n is big theta f of n. Proof. For case 1, we have f of n is equal to big O of n to the power of log base b times a minus epsilon, which implies that f of n over b to the power of j is equal to big O of n over b to the power of j to the power of log base b of a minus epsilon. Substituting into equation 4.19 yields this, which reduces down. The last three series being geometric, since b and epsilon are constants, the b to the power of epsilon minus 1 denominator doesn't affect the asymptotic growth of the g of n, and neither does the negative 1 in the numerator. Since b to the power of epsilon times the floor log base b times n plus 1 is less than this, which equals down to big O of n to the power of epsilon, we obtain that g of n is equal to big O of n to the power of log base b times a, thereby proving case 1. Case 2 assumes this, from which we can conclude that this. Substituting into equation 4.19 and repeatedly applying problem 3-5c yields this down to here. The summation within the theta notation can be bounded from above as follows. Exercise 4.6-1 asks you to show the summation can similarly be bounded. Exercise 4.6-1 asks you to show that the summation can similarly be bounded from below by omega log base b to the power of k plus 1 times n. Since we have a tight upper and lower bounds, the summation is this, from which we can conclude this, thereby completing the proof of case 2. Okay. For case 3, observe that f of n appears in the definition 4.19 of g of n when j is equal to 0, and that all terms of g of n are positive. Therefore, we must have g of n equal to big omega of f of n, and it only remains to prove that g of n is equal to big O of f of n. Performing j iterations of the inequality a times f of n over b, which is less than or equal to c times f of n, yields a to the power of j times f of n over b to the power of j less than c to the power of j times f of n. Substituting into equation 4.19, we obtain this, where big O of f of n. Thus, we can conclude that g of n is equal to big theta f of n, with case 3 proved. The entire proof of the lemma is complete. We can now state and prove continuous master theorem. Theorem 4.4, continuous master theorem. Let a be greater than 0 and b be greater than 1 be constants, and let f of n be driving function that is defined on non-negative all, and let f of n be a driving function that is defined on non-negative on all sufficiently large reals. Define the algorithmic recurrence t of n on the positive real numbers by t of n equals to a times t of n over b plus f of n. Then the asymptotic behavior of t of n, the recurrence, can be characterized as follows. If there exists a constant epsilon greater than 0, such that this equation, then t of n, the recurrence, is this equation. If there exists a constant k is greater than or equal to 0, such that this equation, then t of n is equal to this time theta bound. If there exists a constant epsilon greater than 0, such that big omega of this expression, and if f of n additionally satisfies the regularity condition, a times f of n over b, which is less than or equal to c times f of n, for some constant c less than 1 and all sufficiently large n, then t of n is equal to big theta f of n. Proof. The idea is to bound the summation 4.18 from lemma 4.2 by applying lemma 4.3, but we must account for lemma 4.2 using a base case for 0 to n to 1. Whereas this theorem uses an implicit base case for 0 to n naught, whereas n naught is greater than 0 is an arbitrary threshold constant. Since the recurrence is algorithmic, we can assume that f of n is defined for n greater than or equal to n naught. For n greater than 0, let us define two auxiliary functions, t prime of n, which is equal to t of n naught times n, and f prime of n, which is equal to f of n naught times n. We have t of prime of n, which equals to this, also equals to theta of 1 if this is true, this expression if this is true, theta of 1 if this is true, and this expression if this is true. We have obtained a recurrence for t prime of n that satisfies the conditions of lemma 4.2, and by that lemma, the solution is t prime of n is equal to big theta of n to the power of log base b times a plus the sum of this, right, from these values for j. To solve t prime of n, we first need to bound f prime of n. Let's examine the individual cases in the theorem. The condition for case 1 is f of n is equal to big O of n to the power of log base b times a minus epsilon for some constant epsilon greater than 0. We have this. Since a, b, and n naught and epsilon are all constant, the function f prime of n satisfies the condition case of the function f prime of n satisfies the conditions of case 1 of lemma 4.3, and the summation equation 4.18 of lemma 4.2 evaluates to this. Because a, b, and n naught are all constants, we now have t of n is equal to big theta and log b a, right? Thereby completing case 1 of the theorem. The condition for case 2 is f of n is equal to big theta n to the power of the, right, is this, for some constant k greater than 0 or equal to 0. We have f prime of n, which reduces down to here by eliminating constant terms. Similar to the proof of case 1, the function f prime of n satisfies the condition of case 2 of lemma 4.3. The summation in equation 4.18 of lemma 4.2 is therefore big theta, right, of this expression, which implies that the recurrence t of n is equal to this, which proves case 2 of the theorem. Finally, the condition for case 3 is f of n is equal to big omega of this for some constant epsilon greater than 0, and f of n additionally satisfies the regularity condition for all n values greater than or equal to n naught, and for these to be true. The first part of case 3 is like case 1, right? F prime of n equals to this, which reduces down to here. Using the definition of f prime of n and the fact that n naught times n is greater than or equal to m naught, right? For all n greater than or equal to 1, we have for n greater than or equal to 1 that this is equal to c f prime of n. Thus, f prime of n satisfies the requirement for case 3 of lemma 4.3, and the summation of inequality 4.18 of lemma 4.2 evaluates to big theta f prime of n, yielding t of n equals to big theta f of n, which completes the proof of the case 3 of the theorem and thus the whole theorem. Wow, that was a lot. So the Akrabazi method is here on page 115, and the chapter finishes here. These are problems, practice problems, 119. Okay, we'll read one more section and we'll finish out the chapter here. Sweet. I need to go back through and take notes on that section for sure, though. That was complicated. Honestly, it's not really like that. Like it said at the beginning, like people often like skip this section because it's just the math behind the proofs of these. So if you're interested in the math, which I kind of am, I am interested in it. I don't really have a super in-depth knowledge of kind of following this math. I'm kind of skimming through it, as you can probably tell, but I do kind of want to skim through it to kind of, if I do need a reference back in the future, I want to be able to know where it's at least, right? Okay, 4.7, Akrabazi recurrences. This section provides an overview of two advanced topics related to divide and conquer recurrences. The first deal with technicalities arising from the use of the floors and ceilings and the second discusses the Akrabazi method, in which involves a little calculus for solving complicated divide and conquer recurrences. In particular, we'll look at the class of algorithmic divide and conquer recurrences originally studied by M. Akra and L. Bazi. These Akrabazi recurrences take the form of T of n is equal to f of n plus the sum of, for values of I equal to 1 up to some value of k, a sub I times T of n over b sub I, where k is a positive integer. All the constants a1, a2, up to a sub k are within, right, the set of real numbers and are strictly positive. All constants b1, b2, b up to bk are within the set of real numbers and are strictly greater than 1. And the driving function f of n is defined on sufficiently large non-negative reals and is itself non-negative. Akrabazi recurrences generalize the class of recurrences addressed by the master theorem, whereas master recurrences characterize the running times of divide and conquer algorithms that break a problem into equal-sized subproblems, modulo floors and ceilings. Akrabazi recurrences can describe the running time of a divide and conquer algorithm that break a problem. Akrabazi recurrences can describe the running time of divide and conquer algorithms that break a problem into different size subproblems. The master theorem, however, allows you to ignore floors and ceilings, but the Akrabazi method for solving Akrabazi recurrences needs an additional requirement to deal with floors and ceilings. But before diving into the Akrabazi method itself, let's understand the limitations involving in ignoring floors and ceilings in Akrabazi recurrences. As you're aware, algorithms generally deal with integer-sized inputs. The mathematics for recurrences is often easier with real numbers, however, than with integers, where we must cope with floors and ceilings to ensure that terms are well defined. The difference may not seem to be much, especially because that's often the truth with recurrences, but to be mathematically correct, we must be careful with our assumptions. Since our end goal is to understand algorithms and not the vagaries, how do you pronounce that word? Vagaries. And not the vagaries of mathematical corner cases, we like to be casual yet rigorous. How can we treat floors and ceilings casually yet still ensuring rigor? From a mathematical point of view, the difficulty in dealing with floors and ceilings is that some driving functions can be really, really weird. So it's not okay in general to ignore floors and ceilings in Akrabazi recurrences. Fortunately, most of the driving functions we encounter in the study of algorithms behave nicely, and floors and ceilings don't make a difference. The polynomial growth condition. If the driving function f of n in equation 4.22 is well behaved in the following sense, it's okay to drop floors and ceilings. A function f of n, defined on all sufficiently large positive reals, satisfies the polynomial growth condition if there exists a constant n caret which is greater than 0, such that the following holds. For every constant, right, we're getting into some Greek notation here. What are these symbols? I don't know these symbols. Oh boy. This definition may be one of the hardest in this textbook to get your head around. Okay, hold on. For every constant greater than or equal to 1, there exists a constant d that is greater than 1, depending on that constant from before. such that f of n over d is less than or equal to f of this Greek symbol times n, which is less than d or equal to d times f of n for all values of 1, which is less than or equal to that symbol, which is less than or equal to this constant. Yeah, this chapter is pretty brutal, Mr. Tim. We're almost done with chapter 4, though. We're just toughing through the last couple of pages. This, like I said, this stuff isn't really super relevant to, like, it's kind of like, it's nice to know about, and kind of, if we want to get into the math later on, we can, but I just want to be able to get through it here so we can reference maybe where it is later in the future, but yeah. This definition may be one of the hardest in this textbook to get your head around. To a first order, it says that f of n satisfies the property that f of theta of n is equal to big theta of f of n. Although the polynomial growth condition is actually somewhat stronger, see exercise 4.7-4, the definition also implies that f of n is asymptotically positive, see exercise 4.7-3. Examples of functions that satisfy the polynomial growth condition include any of the functions of the form f of n is equal to big theta of that expression, where alpha, beta, and gamma are constants. Right, that's gamma, right? I think that's gamma. Yeah, it's not lambda. I think it's most of the polynomially bounded functions used in this book satisfy the condition. Most of the polynomial bounded functions used in this book satisfy the condition. Exponentials and their super exponents, exponentials and super exponentials do not. See exercise 4.7-2, for example, and there also exist polynomial bounded functions that do not. Geez, this chapter is brutal. Floors and ceilings and nice recurrences. When the driving function in Akrabazi recurrence satisfies the polynomial growth condition, floors and ceilings don't change the asymptotic behavior of the solution. The following theorem, which is presented without proof, formalizes this notion. Theorem 4.5. Let T of n be a function defined on the non-negative reals that satisfies recurrence 4.22, where f of n satisfies the polynomial growth condition. Let T prime of n be another function defined on the natural numbers also satisfying the recurrence 4.22, except that each T of n over b sub I is replaced with either the ceiling or floor of that value. Then we have T prime of n equals to big theta of T of n. Floors and ceilings represent a minor perturbation. I've never read some of these words before. This chapter is really getting into the weeds of it. Floors and ceilings represent a minor perturbation to the arguments in the recursion. By inequality 3.2 on page 64, they perturb an argument by at most 1, but much larger perturbations are tolerable as long as the driving function f of n in recurrence 4.22 satisfies the polynomial growth condition. It turns out that replacing any term t of n over b sub I with t of n over b sub I plus h sub I of n, where the absolute value of h sub I of n is equal to big O of n over the log of the power of 1 plus epsilon times n. For some constant epsilon is greater than 0 and sufficiently large n, leaves the asymptotic solution unaffected. Thus, the divide step in a divide and conquer algorithm can be moderately coarse without affecting the solution to its running time recurrence. Hey Sri, welcome back in tonight. Hey, what's going on, script? The Akrabazi method. The Akrabazi method, not surprisingly, was developed to solve Akrabazi recurrences 4.22, which by dint of theorem 4.5 applies in the presence of floors and ceilings or even larger perturbations, as just discussed. The method involves first determining the unique real number p such that the sum of I equals 1 up to some value k of a sub I over b sub I to the power of p equals to 1, such a p always exists when p is approaching negative infinity, the sum goes to infinity. It decreases as p increases. It decreases as p increases. And when p approaches infinity, it goes to 0. The Akrabazi method then gives the solution to the recurrence as this. As an example, consider the recurrence t of n is equal to t of n over 5 plus t of 7n over 10 plus n. We'll see the similar recurrence 9.1 on page 240 when we study an algorithm for selecting the ith smallest element from a set of numbers. This recurrence has the form of equation 4.22, where a sub 1 equals to a sub 2, which equals to 1, b sub 1 equals to 5, b sub 2 equals to 7 over 10, and f of n equals to n. To solve it, the Akrabazi method says that we should determine a unique p satisfying 1 over 5 to the power of p plus 7 over 10 to the power of p equals to 1. Solving for p is kind of messy. It turns out that p is equal to 0.83978, dot, 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 and so on. But we can solve the recurrence without actually knowing the exact value for p. Observe that 1 over 5 to the 0 plus 7 over 10 to the 0 is equal to 2, and 1 over 5 to the 1 and 7 over 10 to the 1, sum to those together, is equal to 9 over 10. And thus p lies in the range of 0 to p to 1. That turns out to be sufficient for the Akrabazi method to give us a solution. We'll use the fact from calculus that if k does not equal to negative 1, then the integral x to the power of k dx is equal to x to the power of k plus 1 over k plus 1. Right, I believe that's integral, right? We'll apply with k equals to negative p, which is not equal to negative 1. The Akrabazi solution 4.23 gives us this, which reduces down to big theta of n for t of n. Although the Akrabazi method is more general than the master theorem, it requires calculus and sometimes a bit more reasoning. You also must ensure that your deriving function satisfies the polynomial growth condition if you want to ignore floors and ceilings, although that's rarely a problem. When it applies, the master method is much simpler to use, but only when subproblem size are more or less equal. They are both good tools for your algorithmic toolkit. Interesting. Did you buy that shirt? Is that what you're saying? No way. Who bought that? It was one of our testing shirts. Better not have. Yeah, don't buy that. Not yet. We're like kind of relaunching. uh, we are trying to. They're part of my testing stuff right now. Those first 6 items. Shree, what's going on, dude? All right, this brings us to the exercises and problems for the end of the chapter here. So definitely going to need to be going through the problems at this chapter. This one was pretty brutal. Chapter 4 about divide and conquer algorithms is pretty lengthy. I've got over 100 lines of just notes here, and I need to get more. So probably close to over 200 lines of notes taken here for just this chapter alone, not including any exercises completed. So anywho, let me go ahead and do a little sign off here for the YouTube video. All right, guys, this was chapter 4. Let me go scroll back up here. All right, everybody, this was chapter 4, Divide and Conquer, from Introductions to Algorithms, CLRS, 4th edition. Hope you enjoyed this read aloud version. I hope you enjoyed this read aloud. Thank you guys so much for watching. I'll see you in the next one. Cool. That's all we need. Stop recording. Nice. Okay, so those last 2 sections were brutal. Oh my goodness. This chapter honestly was pretty tough compared to some of the previous chapters. We're definitely ramping it up here, boys. Definitely ramping it up here. Chapter 5. What is chapter 5 about? Hopefully it's not anything terrible. probabilistic analysis in randomized algorithms. Oh boy. What do you guys think? How's everybody doing? How's everybody's studying going? What are we working on today? Probably going to be a little bit of a shorter stream today, as we did a long one yesterday. We did like 3 hours, and I stayed up pretty late last night, so I definitely need to get some better sleep tonight. So I appreciate you guys being here. If you guys could, do me a favor and just smash a like on the stream right now. I appreciate it. I know this wasn't the most entertaining stream for the most part at the beginning here. We were just going over reading the last two sections here from chapter 4, but we had to get through the book, and we have better topics coming. So you guys, I started watching this video. Hold on, let me show you here. I'm not really feeling that good. I'm getting like sniffles. I might be coming down with like a cold or something. 70 leak code problems, 5 hours, right?
So in this video, we will be...
So I started watching this and taking some notes, and I think it'd be fun to go through, whether it be on stream or independently. Because I've worked through quite a few leak code problems, over 100 so far, but honestly, dudes, I have no really like recollection of the exact methods and methodologies for solving the problems. Yes, I did solve them, but if you ask me to go back and solve them, like I don't think I could really do it again very quickly, because I don't think I actually learned the methodology behind the problem, like the true core functionality for some of the easier ones that just require like a set to get rid of duplicates or whatnot, then those ones are fairly straightforward. But like obviously for like the medium problems, like I sit there and I twiddle my thumbs and I don't know what to do, because I'm kind of attributing it to this lack of like real study effort for learning these whatever patterns. So I started watching this. I'm going to take some notes here, and it was pretty good so far. I think what we're gonna do, I want to see if I've done these ones. These first two. These are the only first two I've watched so far. I want to just see. Hey! Thank you, Campbell. Absolutely. Thank you, dude. Aravind Campbell, thank you so much for the sub on YouTube. I appreciate you so much. You're the man. You're the bomb.com. Oh, that was really loud. Let me go to here. My leak code. I'll go get. Okay. Let me see here. Let me look up on the problem list. I think we've already done this. 217. Yeah. So this one's really easy, right? Given an integer array of numbers, return true if any values appear at least twice in the array, return false. We can just create a set of the numbers and compare length, right? It's really easy that way. This one I do remember. So you just say return set nums equal to nums, but we would do length nums, length set nums, right? Contains duplicate. Return false if every element is distinct. Return true if. Am I trolling? We set the nums. We take the length of the set nums. If that changes, we return so do we need is it not equal to the opposite? Yes. You return true if any values appear twice, right? So because the values do not equal the previous, meaning we found duplicates, we would return false, right? Or sorry, true, whatever. Okay, that one wasn't that bad, right? Not too shab on that. Now the next one here I wanted to try and see if I've done in the past. Missing number. Ba-dum. Now I already looked at the neat code list. I don't really care for it that much. I don't know. I like doing. I mean, yeah, we can like cherry pick some. I don't know, whatever. I know, it's whatever. I kind of like the. I don't know. I'm being stubborn. 268. I have solved this one. Given an array of numbers containing n distinct numbers in the range of 0 up to n, return only the number in the range that's missing from the array. Okay. So we have a range of numbers up to some value, the maximum, and there's a value that's missing in there. Since n is equal to 3, there are 3 distinct numbers. And we're not given an n, we're only given a nums. Okay. Containing n distinct numbers. Oh, so it's just the length of numbers is n. Okay, got you. So all the numbers in the range of 0 to n return only a number the range that is missing. Okay. So we could sort, right? We could sort and then go, that'd be n log n in the worst case. Sort and find and just break when you find the part that doesn't equal the next value. Um, So return only the number in the range is missing, right? So now, do we really want to sort? Is that the best bet? So if we go across the 3, what about if we sum, right? So if we know this gives us 4 being 0 indexed, right? We know we have a length of 3. So let me grab a whiteboard. So what if we do a little bit of math? So we know we have a length of 3. And in that case, you can have 0. The maximum value you can have okay, so what is the maximum sum you can have? Well, the maximum you could have would be 3, 2, 1, which would be 6. Right, so the maximum you can have is 6 for a sum. And in this case, we have 4, so the difference is 2, and that's our found value, right? So what kind of relationship does n play to here? It's not 2n, is it? So if we had, let's take another example here. So up to 9, right? 0 to 10, right? For a range. Now, this can have every number summed together. I'm not going to do this math in my head right now. It's too late for this. This length is 1, 2, 3, 4, 5, 6. Length of 9. Meaning that we distinct numbers up to n. Okay, 3 distinct numbers in a range of 0, 2, 3. Things index. Okay. They do include that value. Interesting. Right. So if you sum in the worst in the like the case where you get the most points, obviously the 0 is missing. Oh, so for every value, you just add in the next number, right? The previous plus 1. So that's kind of like the pattern, is that you take the max plus 1, or I guess it would be n plus 1, gets stuck onto the end of the for the next iteration, right? Because if you had if your n is 9, right? In this case, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 distinct numbers, right? The sum you can get for this now this sum here is 44. Or no, sorry, is 45 minus 8 is, what's this one? It's 37, right? So obviously the difference is what you would need. So if we just take each value and sum it together as we go down, would that accomplish our task here? Less than, right? So if we just start linearly and take the 9, pick it up, sum it to the next value 6, sum it to the next value of 4, sum it to the next value of 2, plus 3, plus 5, plus 7, plus 0, plus 1. That takes us to 37. And we know that we have a length of 9. And in the maximum case, we have not 2n, because, right, it would be 45. Right, it would be 45 is the number we're looking for. So how can we get from 9 to 45? Obviously, there's a factor of 5 in there. So if you sum all of these, you get 37, obviously. And then if you add 8, you get 45. Now, if we include the missing digit in like our length calculation of like, so this is 9, but really with the missing digit, it's 10 if we're counting 0. And plus 1. So how can I predetermine the maximum that should be in here? By finding the max of numbers. Going through once, finding the max and the sum. Because we're 0 indexed, should we subtract 1 from the n value? Right, so could we do like for, we'll say m is equal to, or say is equal to, we can probably just do it in one single pass, so we'll just say I don't really want to do this. I can do like a float, like what, negative inf, something like this. And say for, and then we would say n is equal to the length of nums. And then we would, trying to delete your message, one of those guys that thinks he's a know-it-all. Move, boom, gone. Nobody look at that. Okay, so then if we say for num in nums, if num is greater than max, num will be equal to max. Right, so we find the maximum, but then we're also going to sum across the numbers. So sum is equal to 0, and if we say sum plus equal num, now if we say return oh sorry, right, and then if we return what did I say? I said if we return the sum, which is 37, less than, or plus n, 37 plus n, which would be, I don't know, would this work? Would it be sum don't think so. Maybe that works in that single scenario. Like in this case, you get a sum of 4, right? N is 3. So you would return sum of 4. Sum of 4 plus N minus 1. No, so that would, obviously that wouldn't be it. 4. So we need to determine the sum of the array and the, man, that's why I suck at these things. We determine the sum of the array, so this is obviously 4, length of 3, plus 1. So then in this case, we have a length of 9, adding to, making it 10. Sum would be 37. No. Huh. Gosh dang it. So we would have to take gosh dang it. And so if it's so if we have n, we're saying that this is, so we want to get the max and length, and then we determine, right, so the don't want spoilers, please. We're solving it independent. Remove. Bye. So, trying to think. Let me grab my notepad. I keep getting the sniffles, man. I think I'm coming down with the cold. I can feel it. Ah, so sickly. No. Okay, so obviously we need to we're obviously needing to do something with the sum of the array. We know that, and obviously a length here. So you have 3, right? 3 is our n in this first scenario. So n is equal to 3, and our sum is equal to 4, right? So if we say n times 3. So if we do the, right, because we know that the next number in the array, the largest value that could potentially be, gives you the maximum. So if we say 3 times 3 plus 1 over 3, that gives us a value of 4, which doesn't, that gives us the maximum. Then we take the sum. Well, the maximum that can be made is 6 in this case, right? So if we make this 3 times 4 plus 1, I think it was 5, 15. No, not 15 over 3. No, not that one. So if we say obviously we're going to use, we need to figure out the total given n containing n distinct numbers. So 3 distinct numbers starting from 0. So you technically, in both of these cases, they gave us the, right, yeah, so actually in this case, here's the case where the maximum is the missing value. So for an n-size array, the maximum we can find in it is, we have to determine that is maximum we can have is 3 here, because what if we had the 2 and the 1 and the 0 was missing, right? So the length of this is 2. 2 plus, so the length of this is 2. The length of this is 2. And if the 0 was missing out of here, and so the maximum we can make out of this is 3 for a total sum of the array. It should be 2 times 2 plus 1 over minus 1. That would be 6 over, no, so this would be 2. That would give us 2 times 3 over 2, 6 over 2, which is just 3, right? So, and then this case, this was n is 3. Well, that would give us 4. The maximum we can make out of this is 6. Right? Maximum we can make out of this one is 6. So we have 3 times, we did n minus 1 at the bottom. That would take us to a 6. But on the other case, 2 times 2 plus 1 over 2 less than 1 would equal to 6 over 1 gives us 6, which is not true there. And this case, for 9 times, maybe it's not 9 plus 1. Maybe is it less than? So that'd be... No. No, not that either. What is it with people's like desire to just post like I'm clearly working through the solution here. Is it like a online like ego thing? Like does it make people like feel good to oh I don't know. There's like really no benefit. Yeah, so if we have in the first case I take the 3 as our n times n plus 1. Now that would take us to 4. Right. Now if we have, in this case, a length of 2, 2 times 2 plus 1 over, now is it statically always 2 on the denominator? Potentially. So if we say, that's going to be 6 over 2, which is 3. So that one checks out. Now in this case, 9 times 9 plus 1 over 2. This takes us to 45. Okay, so the formula of n times n plus 1 all over 2 gives you your total sum of the array that you could potentially find. Now I guess what you could do is you could go through this and find the maximum. This is length of 9, so the maximum will be 9. No, this is length of 2, so the maximum equals the length. And then you could just go through, and sum while you find a maximum. Right, okay, we found a maximum of 9 here, and we also found a sum. Right, so you would just do n is equal to length of the nums list. And then what you would do is take total sum. So total is equal to n times n plus 1, right, or 2. Now does this always work for even or odd n? So if n is 2, times 3, 9, 25. It's always a whole integer. 6 times 5 is 30, divided by 2 is 15. 7, 8 times 7. Right. something like this. And then we just do something like that. Bada bing, bada boom. Mr. Worldwide, just step in the room. That's what I'm talking about. Enquete, I clearly deleted your message for a reason. People don't get the schmemos. Cool. So let's watch this one.
Useful for when you're practicing later and you keep coming back to do the same question and you don't want to come over here and read the whole dialogue. So it tells us, given an array of nums containing n distinct numbers in the range 0 to
So
n,
let's go over this one. Let's think about it really quickly. So obviously we use some sort of formula here. Now I know we've seen this formula. This is familiar now that I've wrote it out here and figured it out. We have seen this formula in our book. This comes up quite often, as Tim alluded to. This does come in quite. So is this the? So this is just a formula for computing basically a total sum of the array. What is his?
Only number in the range.
Is it a data structure he's going to? What's his little tool?
Here we have 301 and the output is 2. So it looks like we just return the missing number. However, we also need to be careful here because the question tells us from 0 to n. And we can see in the second example that we are looking at the length of the array. So if we have two numbers in the array, 0 to n becomes 0 to 2. And we want every number 0, 1 and 2, even though it looks like this is a complete array here from 0 to 1. Initially, I created this solution where I sorted the numbers and looped through the enumerated list. This gives us I and v, where I is the index and v is the value inside the loop. So for this example, in each loop, we would sort the list, and at index 0, we would have the value 0, at index 1, we would have the value 1, and at index 2, we would have the value 3. So next I have an if statement to check if I is not equal to v, because at some point the value would be 1 greater than the index. And at that point, we can return the value that should have been at that
Fair
index.
enough. So what he's doing there is just sorting the list, so it goes 0, 1, 3, and then comparing the index value over with the enumerate function, right? This gives you the index and the value you're looping over. Comparing the index value to the value, and if those aren't equal, then you have a misplace, right? He's just using the indexes as the checkered because they should be equal in the sorted. Okay, that's a fair
solution. Would have worked also. And finally, we can cover the edge case in example 2. This solution is n log n, which is relatively slow. And the reason being is that sorting in Python is n of log n. And so that slows our entire solution down. Otherwise, the rest of it would have been linear. And we can see from the submissions that I made how slow my initial solution was in comparison to others. A better solution would be to take two values, the first value being the expected sum of our list, and minus from it the actual sum of the list. And the difference will give us the missing number. And to get that...
Okay, so you take the length of numbers plus 1 to increase it to the length of the size of the numbers would be with the missing number there. You get the range. You make a range object of from 0 up to that new length, and then you sum so you take the length of numbers, which would be like 5, you add 1 to it, right? That becomes 6. You take a range, so that becomes 0 to 6, and you sum that. Okay, so that gives you... Oh, okay, that's cool. Okay, so that's doing the exact same thing we're doing here, right? So he's taking the range of numbers times that new length, right? That new length of numbers, right? It's just the same thing. But this case, he's having to sum twice over lengths of n size. So this would be like, right, 2 times n.
that first value, we
Not
take
ter-
the
not
length of the list and plus 1 to it. The reason we plus 1 is because next we take the sum of the range, and the range.
Which one do you think is genius, Tim? This one here? Yeah, this one's pretty clever. So rather than, if you didn't know this little math tool, if you didn't work through this like I did on paper here. There you go. Try in some different options, and then I just put 2 in the denominator with no minus, no subtraction in the denominator. It checks out. And so what you can do is just you can take a new array of one greater size, so as if you filled in the missing number into nums, right? So 0, 1, and 2 now, right? Now you just have because this is a range object with just one missing element in the range, right? You take the sum of that range object. It's pretty simple. Man, this is easy. See, that's what I'm talking about, these problems. I'm like,
The range in Python excludes the last value, so range 3 would only give us 0, 1, and 2. If we plus 1 and take range 4, that would give us the expected range, which is 0, 1, 2,
why you
3.
need length plus
So we
1.
add 1, take the range, and the sum. From there, we have our value and can do our calculation to find the missing number.
Hey!
And this gives
I can't pronounce. I'm not even gonna give it a try. Thank you so much for the sub, dude. Appreciate you so
us
much.
an O of n answer, because you can see in my notes the relative time complexity it takes for each operation in this solution. If our list or input grows by double, for example, we only have to do double the additions, and so this summation here would be our bottleneck. I'll put on the screen a good explanation on doing more of the same operation in a linear fashion, and how we can look at multiple operations in the same solution to figure out the time complexity. So bear in mind that doing multiple O of n operations sequentially, like we have here, and not nested in the same
just
algorithm
added.
or solution, would still equal O of n.
Right,
And so
it's
that's
just
our solution for the missing number.
We would just drop the constant, right? Right, you're just summing multiple runs over n, not nested. You're right, you're not doing an iteration of, in the worst case, of n on n, right? You are doing a pass through n, stopping, evaluating that pass through n through another pass through of an equal size of n, and comparing, right? So it's a summation, not a multiplication, right? That formula derived is the triangular number. A triangular number. The triangular number, okay, so a triangular number or triangle number counts objects arranged in an equilateral triangle. Triangular numbers are a type of figurative number, other examples being square or cubes. The nth triangular number is the number of dots in the triangular arrangement with n dots on each side, and is equal to the sum of n natural numbers from 1 to n. Okay. So it just creates this kind of triangle then based on the amount of objects you're finding, right? It's for every new next layer, you have one less value than the previous, creating this kind of triangle structure, right? So it's given by this formula, right, that we derived here, n times n plus 1 over 2. For a binomial coefficient, it brings the numbers of distinct pairs can be selected from n plus 1 objects, and it reads aloud as n plus 1, choose 2. The fact that nth triangular number equals to this can be illustrated using a visual proof. So how does the triangle like shape kind of it's kind of beside the point, Mr. Tim. How does the triangle shape kind of play into our array? Like in terms of like, is there any sort of like geometric shape orientation that you can like? Is anyone trying? Is picking up what I'm trying to say? Like, is there any like? Could you tell? Let's ask. Learn about triangle number. I solved LeetCode 268 missing number by computing the total sum that can be contained within a n size array of range 0 to n. And so I derived the formula n times n plus 1 all over 2. This also resembles the triangular number formula for computing objects arranged in an equilateral triangle. Now, is there any, this kind of is a little bit abstract, but is there any kind of physical or geometric orientation with the array that we can derive using these triangles? I'm wondering. It's like kind of a crazy question. In fact, you're noticing something very deep about why the triangular number formula shows up in a problem like LeetCode 268. Let's unpack it. The triangle number formula goes so 0 plus 1 plus 2 all the way up to some value n. So the sum of an array or index array, right, or range of values is, n, up to that range plus 1 times n plus 1 over 2. So this is the nth triangular number, the number of objects you can arrange in a triangular grid for n equals to 3, right? Why does this connect to the array? When LeetCode asks for the missing number, the trick is the array is supposed to contain all integers from 0 to n. That's exactly the first n natural numbers sum. Geometrically, you can think of that sum as building a triangular stack of numbers. So conceptually, the missing element is one pebble missing from the triangular arrangement. Physical geometric orientation. Here's where your intuition's right. You can visualize the array sum geometrically. Imagine lining up 0, 1, 2, n blocks in this like a stair. Stack them sideways and you literally get a right triangle of blocks, right, for n4. This shape is 10 blocks, exactly the triangle number. You're summing increasingly numbers index values. Each index contributes to a row. Stony codes. Yeah. I saw this video. I started it today here. We kind of are reminiscing or kind of going back over. We've solved about 100 LeetCode problems so far. But in all honesty, the grind through the process has kind of blurred the actual vision. I don't really remember a lot of the problems I solved. I don't, as you can see, we solved this easy problem probably pretty early on in our um, LeetCode career here, and it took me a good 20 minutes to work back through again. So definitely not like solidifying the knowledge up front for sure. So I figured that this 70 LeetCode problems in 5 hours, every data structure full tutorial could help us to hit probably 70 problems that we've probably already done, right? The odds are we've probably done these, probably pulling like pretty easy examples for these. And then just get more of like an actual study of the method behind the problem. So I started writing this little repository here, LeetCode practice. Um, which he's starting with arrays. So then you have this. So we're gonna have like little chunks here, right? So missing number approach. Approach number one. We're going to. So in our approach here, let's kind of just summarize this really quickly before we kind of wrap up for today. For our studying. So number one. So we did. So computing the triangle. Computing the triangle number. Right, so this is compute the triangle number, which is the sum of the range, the full range, 0 and plus 1, right? Right, because that's excluded, but you would include it on the triangle number includes the n in the sum, right? So then so the triangle number formula is so you would do triangle number equals to n times n plus 1 all over 2, like so, right? And then return the difference between sum nums and or total and sum total. Sum of numbers. Something like this, right? Return the difference between the triangle number I guess I'll just bold it. It's not how you bold. And the sum of nums. Okay. I'm going to take my code here. I'm going to stick it right in here. Right, so you can do this. Compute the triangle number. Or you could just, or this is the same thing as, so I'm going to take this, put this here like so, and then we're going to say, or we'll just leave it at that. Yeah, that looks good. right, let's go ahead. I'm going to take this guy, I'm going to throw it in here and say, what you think? Short clean. Use an XOR trick for comparison. Should I do a time and space? So time complexity would be should just be big O of n. And then space, we're using same numbers and we're not creating any range objects, we're just creating a new variable, so this would be big O of 1, right? Yeah. Let me just take this really quickly. Is this returns so the length of numbers, we take the length, so just a single O of n. But is it just a comparison? Is this O of n or is this O of 1 for time?
Next up in array, I encourage you to do this.
So the set, so even though you create a set, you still have to look at every item. Okay. That makes sense. All right, so this is what my notes look like, kind of how I'm doing it, right? Problem links, takes you to the links. So if you guys want access to these, you guys can find them on my GitHub or in my Discord. So compute the triangle number, sum of the full range. Return the difference between the triangle number and sum of nums. Cool. All right. Nice. Yeah, my nose is sniffling. I'm totally getting a cold. I can feel it. No. Oh, come on. This is brutal. Okay, I just want to get a preview of the next problem. Find all numbers disappeared in an array. So given an array of nums of n integers, so n is our length, where the number is in a range of 1 to n, return an array of all the integers in the range 1 to n that do not appear in numbers. Okay, so this is kind of the same thing, but there's multiple numbers that are gone, and we need to find them all. Okay, so this is kind of similar to his previous solution, right? Where rather than well, that had to sort, right? So his first solution, can you do it without extra space and an O of n runtime? So without sorting. You may assume the return list does not count as extra space. Could you do it without extra space and O of n? Okay. So if we compute the total of this array, right, obviously we have some values missing. Well, I don't want to have to loop back over like the set and figure out like which ones were in, right? Find all numbers disappeared in the array. So if we don't want to do it with sorting, right? In this case, 5 and 6 would give us 11. So in our first solution, we'd be given 11 at the end. And we don't want to be given 11 because that's not a possible value. So let's think back to the previous problem here. We computed the triangle number. What he did he lined up, he created the range object and summed it. So we know in this case we hit the 4, 7, 9, 16, 24, 26, 9, 30. But we have potentially a lot of missing digits, right? You're given an array of numbers of n integers, where the number in the array is within some range of 1 up to n. So what if we take n in this case, which is 1, 2, 3, 4, 5, 6, 7, 8, and it's 8. The sum of the array is 30. Huh. Find all missing numbers. I don't know if I solved this one. I don't think I have. Huh. Right, we could do the sorting thing and then use the index to compare on the sorted array. But now if I bit shift Hey Ray.
In numbers. In this problem, we have to check the given list.
Check the given list for missing numbers in range. Iterate through range and append to new list if not in the given list. Iterate through the range of numbers and append to a new list if it's not in the given list. Okay, yeah, so you say missing. Say for num and nums. I would say for num and range. Now this is in range of 1, right, not 0. For num in range of 1 to the length of numbers, right? Now, the length of numbers in this case 1, 2, 3, 4, 5, 6, 7, 8, but we have an 8 inside. or it doesn't matter. We're index. So for I, right? If I in nums now can I set nums if I in nums miss it? Oh, so you can be given a number range that has duplicates? So the length is 2. So we need to include the 2 in our so this goes 1, 2. I is not in nums. Why does this not? So if we set nums, so if I is not nums, we append the missing value. So the length of this is 2. Oh, hold on. So we need to do the original length. So n is equal to the length of nums. And we need to set n here instead of the set because we don't want to reduce it down. Okay, that solves it. Now we're iterating over a range object, so that's okay. So what do you think, Mr. Sim? Ray, Magnet? Hey, Nisha, how's it going? What's going on, my guy? Okay. I think I'm getting sick. I made a set on nums be fast. Is this still 01? Because replace nums. Nice. The set num takes O of n time and O of n space. Okay, so there is a constant space trick here. Right. There is a constant space trick.
For missing numbers in the range 1 to length of numbers. So this is a nice little reminder for myself because I've seen this question before. But if you've not seen this question, let's read the official description. Given an array nums of n integers where nums I is in the range 1 to n, so essentially we're given a list of numbers that is repeat 1, return 4. Let's go over to our whiteboard and have a look at the solution. This is the nums that was passed in the first example. This means we're going to have the same list as a set where all of the duplicates are removed. And it's not relevant here, but just a reminder that sets in Python are have 2, we already done this, to them. If we do not exist here is 8, so this 1 to 8 list is in our list. In our set, number of, again, numbers are missing, or more numbers missing, would also, I don't think, and is solution, so here it is. And so that covers everything on this find all the missing numbers question. Next up we have, and so that will definitely be useful to go through this constant space and understand, be beneficial to go through. I've also included a solution which had O of 1 space. Right now I don't think it will be beneficial to go through it, but if you're looking to improve your Python skills and understanding of these questions, it will definitely be useful to go through this constant space solution, so here it is.
Okay, so you create a temporary variable for every number in the range length of numbers, and you do the absolute value less than 1. If the numbers at index of that temp is greater than 0, what? Nums at that temporary index variable, it's multiplied by -1.
And so that covers everything on this find all the missing numbers question.
Huh. Sure. Each number in the nums is in the range 1 up to n. That means every number corresponds to a valid index num less than 1. Yes. We can mark a visited position by flipping the value at that index negative. After one pass, any index value and still holding a positive number means the index +1 was missing. Huh. Alright. Cool. So I think this is kind of fun. I like this kind of going through these and trying it on our own and then getting more of a breakdown and learning the actual data structure and pattern behind it rather than just kind of getting the problem done and moving on. I think it could be beneficial for us in our studying. Let me know what you guys think. Thank you guys so much for being here. Sorry I deleted some of y'all messages, but y'all know that we don't like spoilers while we're trying to solve. It really does us no good to just get an answer. I think, that's probably what, if we didn't, I mean, we worked through the problem the first time and we still didn't remember the solution. So getting an answer and just moving on is not going to help us at all. So obviously, anyways, so sorry I delete some of your messages, but you guys, you know the rules. Anywho, I appreciate you guys being here and hanging out with me for tonight. Please join me tomorrow as we'll probably continue on and with our MIT OpenCourseWare problem set 3 from 6.0002, Introduction to Computational Thinking and Data Science. We're on week 8 in problem set 3. We're about to finish up that problem set and move on. So we'll probably take a stab at that tomorrow and then keep working on our project and, keep going here, you guys. So thanks so much for being here tonight, and I'll see you guys tomorrow. Oh, I forgot to start Twitch today. That sucks. That really sucks. Dang it. All right.